Hi kidlets, this is just about your last notes on black holes and neutron stars. So we left off talking about supernova and how supernova release elements into the universe. We have type 1a and type 2. So after a supernova, there are two possible outcomes. You can have either a black hole or a neutron star. And again, mass is the determining factor. So this guy is supposed to be a subscript there. But if you have the stellar core that is less than 3 solar masses, you have your protons and your neutrons, which are unstable, recombining to form neutrons, hence the name neutron star. So the formation of the neutrons halt the star's collapse. And these can be observed as pulsars, which I'll talk about in a moment. But if you have a stellar core that is greater than 3 solar masses, there's nothing that can halt that collapse, and that's where you get a black hole. So they're both a result of a stellar core collapse after a supernova, but mass is your factor as to which outcome you get. Neutron stars are very small. They can be only about 20 kilometers across, and you can see that in this map picture we have a tennis ball that represents a neutron star, and this is a map of Washington, D.C., which is bigger than the neutron star. So these are the most dense things known to exist. Even though we already talked about how white dwarfs are very dense, neutron stars are even more dense. So a piece of neutron star matter could... So if you were to have a piece of neutron star matter the size of a sugar cube, it would have a mass of 100 million tons. So these are very small, like I said, but they have masses of anywhere between 1.4 and 3 masses of the sun, even though they are very small, so they're incredibly dense. So some neutron stars we can see as pulsars. So if you remember back to physics, if you took physics, and you remember the law of angular momentum, as you collapse something to a very small size, that momentum has to go somewhere, so it results in it spinning. So neutron stars spin, pulsars spin. Pulsars is more of the phenomenon that we see as the pulse points towards us. So pulsars are rapidly spinning neutron stars, but all neutron stars are essentially rotating. So you can end up having jets that are emitted from the magnetic poles, not the rotational poles, that are moving at the speed of light. And speed of light is always represented by the lowercase c. So if you look at this lower picture here, you can see that we have the rotational axis, which we would consider north and south, but the magnetic axis is misaligned. So what that results in is, as it is rotating, this beam of light right here could be pointed towards Earth. So if it were pointed towards Earth, we would see it as a pulsation, or a pulse as it's pointed towards us and then moves away. So here is the most famous pulsar. This was the very first pulsar that was actually ever discovered in the Crab Nebula. So this is the Crab pulsar. Here you can see it's on, here it is off, and I'll show you another higher resolution image of that in a moment. So it would appear to pulse as it's rotating towards us. So the fastest neutron star, or the fastest pulsar, is 642 rotations per second, whereas the slowest is 4. And these are always slowing down because once you have that initial collapse of the stellar core, they're going to be slowing down in time. However, there can be situations that can accelerate them, such as if it is in a binary system. So in that case, you can get this huge accumulation of surface material in an accretion disk, the same way you get a nova or a type 1a supernova. But in this case, what you're getting is it's so high energy, you're getting a buildup of gamma rays. So this results in GRBs, which are gamma ray bursts, which can be absolutely devastating to anything in its path. These are far more catastrophic than a supernova, and this is what the Fermi telescope is out trying to detect. So here are some pictures of some neutron stars. So these on the right are real images of the Crab Nebula, or I'm sorry, the Crab pulsar. This is taken by Chandra. This is in the X-ray. I believe that this one is in the infrared. This is a depiction, an artist's depiction of a binary pulsar right here, stealing mass from a red giant star. And I always think these pictures look kind of crazy, but this is a picture of a rotating neutron star and the dipole magnetic structure. So here again is that lighthouse model of a pulsar. So we would only see it as a pulsar if this beam of light happened to point towards us. And again, remember the rotational axis is right here, but the magnetic axis is this way, and that's the way that we would observe it. So just like a lighthouse, when it's pointed towards us, we would see a pulse. So here is the Crab pulsar. This is a remnant from a supernova that's observed in 1050 AD. So it's right here, and here you can see the pulsar winds and jets. So there is the star itself. So here is a jet being emitted. There is another high energy jet.